There might be one thing in the slideshow that's new for you. We'll get to that when we get there. Vertical line test, as it says up there, tests for whether or not a picture is a function. Does that graph denote a function? If you can draw any vertical line through the graph at any point, and it only hits, or it doesn't hit in 2 or more spots, then it is in fact a function. You do this already, correct? Yeah. And then later on we'll talk about the horizontal line test, which does something different. Not a function. A function. What about this guy? Is a function. Because remember, the rule says if it hits in 2 or more spots, it's not a function. That doesn't hit in 2 or more spots. It doesn't have to have stuff on all the x's in order for it to be a function. Some other functions, we talked about these, but here are some pictures of them. You got your standard linear function, you got your quadratic, your cubic, absolute value over there, reciprocal function, the basic sine and cosine, which most of you demonstrated a pretty good understanding of graphing on the quiz, and then you've got some square root functions. Were there any others we talked about that? Oh, the exponential function isn't up here. You know, that guy, the one that goes like that. Logarithmic, which you haven't talked about much, we don't do a lot with. And then the other one is the step function, also known as greatest integer function. It's called the greatest integer function because it takes any number and takes the greatest integer that makes up that number. So if you take a number like 2.718, the greatest integer of 2.718 would be 2, and therefore it would graph 2. What isn't visible in this graph is the open circles and solid dots. On the step function, the left side is a solid dot, the right side is an open circle. Okay, I just stole that off the calculator. And notice the notation. Double absolute value bars represents that step function or greatest integer function. We don't do a lot algebraically with that. We do dabble a little bit with some graphing stuff. We translate that graph, flip it over, slide it around, stretch it, that kind of stuff. Have you dealt with this before?
Nope.
You've never seen this?
Yeah, maybe I have a really bad memory. That could be it also.
Okay, we'll go with that then. Piecewise function. It's a piecewise function, which means it's a function, which means when you're done graphing it, it still has to pass the vertical line test. This one is made up of 3 separate functions. You put them all together and you get one pretty little picture. And we're going to practice sketching this guy. Well, I will. You're just going to watch. There are a couple different ways to graph it. You could graph the entire function and then erase. Some people like doing that. Or you can just graph the part that you are concerned about. So we'll start with the top function, 2x plus 3. What can you tell me about the graph of 2x plus 3, Caroline?
It's a line, and the y-intercept is half straight, and it goes to the supposed to.
Perfect. 1, 2, 3. Y-intercept of 3. I could go up 2 and over 1, but I don't want to because I don't want that part of the graph. Notice it says, uh-oh, what did I do wrong? Colored it in. That shouldn't be colored in. Why shouldn't it be colored in?
Because it's not actually there. I don't want it included.
It's not included. So that should be an open circle. Down 2 over 1, solid dot. There we go. That takes care of that guy. Red is a parabola. Solid dot at 0. Why a solid dot? Because it's less than or equal to over to 2. 2 squared is 4. So 1, 2, 1, 2, 3, 4. Open circle here. And then last but not least, that takes care of that. Last but not least, in a lovely shade of green, we have, uh-oh, what's a graph of 1 look like?
Just a point, right?
What does that mean?
It's horizontal.
Good, it's a horizontal line at 1. And we want it from 2 over. So solid dot at 2. So I'm done graphing my piecewise function. I'm asking myself, does that pass the vertical line test? Does it?
Yes.
Yes, it does. Okay, so if I draw a vertical line, let's say the y-axis, it does appear to touch the graph in 2 spots, here and here. But notice this one is solid and this one is open. That's crucial. This is open, this one's solid. If you have 2 points that are vertically aligned, one of them has to be solid and one of them has to be open, or they both have to be open. can't have them both closed. You good? Okay. What is, whoop, sorry. Not 15. Well, yeah, let's do 15. What's f of 15? Good. What I meant to write is what's f of 1.5? Two and a fourth, correct. 2.25. Why?
Because 1.5 is between 0 and 2, so you square it.
Outstanding. 1.5 is between 0 and 2, so it belongs in this part of the graph. Therefore, you plug it into that part of the graph and only that part of the graph, and 1.5 squared is 2.25. Good. Okay, so it's not a matter of plugging it into every one. It's not a matter of plugging it in only two of them. You have to find the one that it works in and plug it into there. Last example would be something like, what is f of negative 10? Well, negative 10 is less than 0, so we plug it in there. Okie doke?
Yes.
Beautiful. Transformations. We're going to focus on sliding things up, down, left, and right, and flipping them over. Sometimes we'll stretch, but not a lot. Okay, and this is what happens. So on the far left, you can, if it's a number on the outside of the function, it moves up. A positive number on the outside of the function, it moves up. If it's a number inside the function, it moves left and right. A minus sign out in front flips it over the x-axis. And then this one is an example of all of them. And we can just skip ahead to, these are transformations, great. And what am I looking for? That's what I wanted. Nice summary chart for you. Okay, we take a function f of x, regardless of what it looks like. If I add a minus or plus c, it's going to move it up and down. The vertical shifts are going to move it up and down if that number is outside the function. If it's stuck inside the function, then it moves it left and right. And we can reflect it over the x-axis, reflect it over the y-axis, and even if we're feeling crazy, we can flip it over the origin. The nice thing about our trig graphing is that we don't have to worry about any of that because of the system that I showed you the other day where you find your starting and stopping points. This becomes irrelevant. This is more important when you're dealing with functions that are non-trig functions and have to figure out how, let's say, the absolute value of x plus 2 differs from the absolute value of x, graphically. Okay, we good? No? Okay. Okay, let's get to the fun stuff. Come on, where are we? Day 6, great, we're done. Come back to that later. Here we go. Is it safe to assume you can all add, subtract, multiply, divide functions? Good. However, what we might need to talk about is composite functions. F of g and g of f. Composite functions take one function and put it into another function. What you need to be careful with is the notation. You take the right function and put it into the left. You take the right function and put it into the left. And that gives you another function, hence the reason it's called a composite function. So as a quick example, we have a stylus disconnected, and then it's going to jump up to like 3 slides. I told you. All right, so let's go back. Good thing I'm recording this. All right, now let's just stare at this slide for a little while.
Information we'll never get to know.
Okay, that's good. There we go. I can edit that out later. 2 functions, f and g, 2x minus 3 and cosine of x. What is f of g? Boom. Boom. Somebody? Go, how many get?
It'll be 3 times the cosine of x minus 3.
Beautiful. And since you're on a roll, give me g of x also.
It'll be cosine of 2x minus 3.
Well done. Okay, simple. Put one function into the other. Sometimes you may have to simplify it. There's no simplifying involved in these two. They're pretty straightforward. But if the functions get big and scary, you might be able to simplify it a little bit to make your life a little bit better. Now the fun part. Polynomial inequalities. These are a blast. This will come back to you as you watch me work through an example, but at some point you're going to have to test regions, and I will show you. I'm thinking you've never seen this before, but you might have. Your teacher may have showed you last year. Have you seen Boolean Logic on the calculator? Do you have any idea what I'm talking about? All right, I'll show it to you. It might be a helpful tool for you to use. It might just be a pain in the butt, but we'll see about that as we get there. Okay. So, solving a polynomial inequality. First things first, turn it into an equation. Solve that equation. When I solve this equation, I get two answers, 5 and -2. Those become what's called critical numbers. You've heard that phrase before, right? Okay, good. You're going to hear that phrase a lot. It's a crucial concept in calculus, this idea of critical numbers. Those two numbers do something important as related to this function. If it was just an equality, then you solve it, and those critical numbers are actually your answers. In a polynomial function, it's a little bit different. That's going to cause something weird to happen. And that weirdness is called the critical number. So then you take those two numbers and you slap them on a number line. And then you have to test regions, which I already told you the answers, but we'll go through this anyways. Those two critical numbers divide the number line into 3 regions. You need to test all 3 regions. It is a fatal mistake to test one region and assume that it flips back and forth across every critical number. That isn't always the case. Let's start with the easy one. What's a good number to pick in here? 0. Well, 0 minus 10 is -10. Is -10 greater than 0? No, it's false. We don't want that area. What's a good number to test on the left? A jillion. No, not a jillion. -4. Or a negative jillion if we'd like. -4, let's see, that's 16 minus 10 is 6. Is 6 greater than, what did we say, -4? -12. Yes, it is. It's true, so we're good to go. How about a number to the right? 6 is fine. It doesn't matter what number you pick as long as it's to the right of 5. All right. 6 is 36 minus 10 is 26. 6 times 3 is 18. 26 is greater than 18. We're good to go. In a straightforward problem like this, you won't need this Boolean logic thing that I'm going to show you because you're all fairly bright and can plug and chug into a simple inequality. Remember, you test this back up in the original inequality. This looks familiar, right? You've done these?
Yes.
Beautiful. They can get a little nastier. Oh, yeah, by the way, what is this in interval notation? Because we want our answers in interval notation. What is the answer to that problem in interval notation, Michael?
Parentheses, negative infinity to -2, parentheses, the
You need, yeah.
then 5, parentheses 5, positive infinity.
Quick question for you, though. You put a parentheses on the -2 and the 5. Why?
Because the function is in between -2 and 5.
Let me rephrase my question. Why did you exclude -2 and 5?
Because it's not greater than.
There you go. Beautiful. This is a greater than function, not a greater than or equal to, so these are open circles, which means you don't include them in interval notation. Good. All right, now this guy. first things first, before we start solving anything and turn that into an equation or do any rigmarole like that, I have a simple question. What values of x bother you?
0.
No, 0 is okay for me.
5.
Oh.
5? Is that you, anything?
Yeah.
Yeah, why 5?
Because that would make the denominator in the other right equation 0.
Okay, so x cannot be 5, and x cannot be?
Negative 1.5.
I'm sorry, what?
Negative 1.5.
Fraction form.
Negative 3 halves.
Thank you. We'll stay with fractions. That way we don't go down that dark path. So before I started anything, those are possible critical numbers. When I put those on my number line, are they solid dots or open circles? Open circles, because they can never be that. Even though this is a less than or equal to, they're still open circles because they're things that cause a whole bunch of problems. There might be some other critical numbers. How do I find those other critical numbers? I have to turn this into an equation. 2 over 2x plus 3 is equal to 2 over x minus 5. How do I solve that? Cross multiply. 2x minus 10 is equal to 4x plus 6. So bring that over there, bring x is equal to negative 8. Hot diggity. Well, let's just do it. Create a number line. And I don't mean to insult anybody, but make sure you put them on the number line in the correct order. Which is the smallest number? Negative 8. Solid dot or open circle?
Solid dot.
This one's solid because of that guy. Negative 8. Negative 3 halves, open circle, and 5. Open circle. Now we have 5 regions to test. And so let's pick the easy one. Let's start with this guy. Well, maybe the easiest. What's a good number to pick in here? 0. So what happens when you put in 0? Is 2/3 less than or equal to negative 2/5? Who's good with fractions? Well, nobody cares. Why don't we care about the fractions? Yeah, one's negative, one's positive. Is that a true statement?
No.
Well, you got both covered, yes or no?
No.
No, it's not. This is a false region. Now I got 2 others to test. And you can see what's going to happen. If I start picking numbers and plugging them in, I'm going to get some weird fractions that I need to compare. That scares me a little bit. Okay. So we're going to try a different technique. We're going to use this thing called Boolean Logic. So get out your calculators. All right, so here's my calculator. And again, this is entirely up to you whether or not you want to use the Boolean logic. I'll show you how to use it. Some people figure, nah, it's easy, I'll just plug the numbers in myself. Others might say, oh no, this is rocking, let's do that. Just to get back to where we were, I've got that handy. What I'm going to need is this guy. So I need the numbers. What are we going to test over here? Somebody write these numbers down, by the way, because it's going to go away in a second. What, like negative 20, is that okay? How about in here?
Negative 5.
Negative 5 is good, and then over here?
10.
Let's get crazy. Let's put 1,000,000 in.
No.
Yes,
Sure.
watch me. I'm driving
Swing
the
for
bus.
it. Yeah.
Okay, so here's how you do it. We'll start with the left side. We're going to take negative 20 and store that into x. Now, wherever the calculator sees x, it's going to consider x to be negative 20. That's the easy part. Now the hard part, and this is what's going to determine for you whether or not you want to type it into the calculator. But we need to do the following. We need to type the inequality into the calculator. So it looks something like this. 2 divided by, no, that's a times. Ooh, somebody's getting a call.
Oh, I see it. It's the one. It's
No,
the
no,
one.
sorry.
Right.
It's mine.
Hello? I can, Cindy. How are you? Cindy?
I don't think it is. No! That's a spam one! No, 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 no!
Hi. Hi, Cindy with Florida Getaways. Yes, I can.
This
Cindy?
ghost that keeps calling me out.
No. What?
Okay, I'll make it up.
Going on a vacation.
No. All inclusive? And an entertainment package.
Yeah.
Did you stay at one of their resorts in the past?
What resort?
RCI or something international. No blackout dates and you can travel. Okay. All right, go ahead. Go ahead, transfer me. Yeah, okay.
Greedy. Put it down. I don't want any more spam calls. Can't you block them all?
Okay.
I already have 5. I can't block more than
Yes.
5 people.
If you say don't call me anymore, they technically are not allowed to anymore. Like,
It's been taken out from your call list.
Does your
Yeah.
family make at least $50,000 or more?
Sure.
Yes.
Your family's gonna get paid. Yeah.
Yes.
Rachel, airplane mode, got it.
And almost all resorts require a credit card as well. Do you have a major credit card?
that's so cheesy.
Yes.
Back to the lesson.
You do qualify, and just a reminder.
'Cause I have a pulse.
Just basic food and lodging, and even drinks in most cases. So relax, have fun, and don't forget to pack plenty of sunscreen. Do I have your permission to transfer you over to a travel specialist who can cover all the details?
Yes.
Okay, great. Gonna transfer you now. Hold the line, please.
Thank you.
Hi, my name is Mary, and I'm a resort specialist here at Cancer Tree Vacations. How are you today?
Great, how are you?
I'm well. Who do I have the pleasure of speaking with?
This person's math teacher.
A math teacher?
Yes.
Okay. What do you get?
I'm sorry.
Add this plus...
Oh, I should just hung up.
Only I would get hung up on by a crappy business call. Holy smokes. Somebody go get the dog. I'm gonna need to pet the dog. Oh, that's horrible. I am not gonna get over this easily. 2. Which one's divided by? It's the top one, right? Divided by. Okay. Now, be careful when you're putting in rational functions that you put, like in this case, we're going to put the denominators in parentheses so we don't screw it up. And it was 2x plus 3. X plus 3, close parentheses. Come on, close parentheses. There we go. Okay, these guys, the greater than, less than, greater than or equal to, or less than or equal to, are under the test menu, which is above math. So you go second, math, and I forgot which one we had. Which way is it going?
6.
Less than or equal to, right? Okay. 6. Then we had 2 divided by parentheses, and the bottom was x minus 5.
Wait, you don't have the 2. Wait, just gonna start.
Don't confuse me. I'm easily distracted, as you can see. Now hit enter. You're going to get only 2 answers, 0 or 1. 0 means false, 1 means true. So you can see that that's kind of a pain in the butt to type in the function. But you only have to type it in once. So now what was the next number we were going to test? -5, I think it was?
Yeah, sure.
Okay, so all you do is -5, store x, enter. And then you use your little up arrow and come up here back to the function that you already typed in and hit enter. And then hit enter again, true. Okay, so again, the advantage of having only typed the function in once and being able to use it over and over again to test a large number of regions might prove to be beneficial on the calculator.
Wait, how do you get the equation back? So,
How do I what? I'm sorry?
How do you get the equation
You
back?
just click on it, like this.
Yeah, you arrow up to it and then hit enter.
It doesn't work for me because I have an old.
Then you do second enter until it comes back up.
Doesn't.
I don't know what to tell you.
Press it.
Hit second enter again. It'll keep going all the way back through what you typed in.
No, it doesn't. It does the same thing over and over again.
Time for a new calculator. I don't tell you. Okay, got it?
Yep.
There was one other region we didn't test. I'll leave that up to you. But again, since you already have it typed in there, you can go back and test this. The other option would be to just do what we did on the first example and type those numbers, or do the numbers in your head over and over again.
Okay, so.
It's funny, it's not
She probably was like, this plus